Any question about the previous session? Today we want, first I should apologize for the problem with my office hour yesterday. We will have an office hour immediately after this class and also on Friday, as I advertised in the comments. Sorry for the problem. Okay. We have started our discussion about the energy-based models, and today we want to talk about contrastive divergence. Okay, we know that they are very flexible models because they just need a mapping from your observed data space into a real number. This real number represents the probability of your input, but we have severe problems. The first problem, which was easily solvable, was that the output must be positive. It is easy, but the severe problem is that the output, the area under this curve must be equal to 1, which is the property of a valid PDF function. And we see that the second one is very hard to solve, and there are challenges for that. We have seen two methods to sample from them, from a trained model, and then we start the contrastive divergence to see how we can train them. Okay, here is the last slide. We start. Previously, we observed that if you want to calculate, if you want to update your model parameters so that you give high likelihood to the data, to the training data samples, in order to train your model, you need two terms. The first one is minus, let me write down, the gradient with respect to the model parameters of the log likelihood equals two terms. The first one is minus the gradient with respect to the model parameters of your energy function. It means that you should go to the direction such that the energy is going to be minimized, and also minus the gradient with respect to the model parameters of this z theta. And we know that z theta is not a function of your x. It is not a function of x, but it is a function of theta, and in this place you need the gradient of that value, this value with respect to the model parameter, which is interactable in the general case. So the first part is very easy. You can calculate it with one model.grad in any of the, for example, libraries in Python. But the second one is challenging. But we see that the second one can be casted as an expectation. It means that this second one, the logarithm of this z theta, can be casted as an expectation or data coming from the model. This is the first difference. This is the first major difference with our previous expectation we generally see in this course. What is the difference? We generally calculate the expectation with data coming from the true data distribution. For example, when calculating the likelihood or anything. But here, you need to calculate the expectation with respect to data coming from the model distribution. If this model is, for example, a GAN, so it is easy because sampling a GAN is just one forward propagation. But sampling an energy-based model is very time-consuming and hard. Why? What? Yeah. We introduced two different algorithms to sample from this. What are those algorithms? Yeah, the first one was Metropolis testing algorithm, and the second one was exactly HMC. Hamiltonian Monte Carlo, that we talked just about the Langevin Monte Carlo. LMC, or another name was MALA. These are two methods that can bring you samples from this distribution, and then you can calculate this expectation. But the problem is that you cannot estimate, or you cannot understand when these two algorithms are converged to the true data distribution. So you need to stay for a long time to be more confident, and then you have severe problems for just sampling one sample from this p theta distribution. So the change from the p theta to p theta is very challenging here, because the model you are using for your model distribution is energy based, and in energy based model you cannot sample easily. Okay? Now we want to talk about the contrastive divergence. Contrastive divergence is a method to mitigate this problem. Okay. We have talked about this part. Now we don't in CD you will see that we do not need to calculate this gradient anymore, and also you need to sample you need to use samples coming from, for example, Metropolis testing or LMC. But the point is that you can use the samples of these algorithms in a predefined iteration. It means that you can have just one iteration over each of these algorithms, and then use the resulting x1, which is the output of the first iteration. So it is much more simpler than sampling from the true model distribution. Okay, we just have two definitions here, which is needed throughout our discussion about CD. The first one is that if you start any of the algorithms, for example, MALA or Metropolis testing, or there are lots of Monte Carlo algorithms, Markov chain Monte Carlo algorithms for sampling, but these are the two that we focus on in this course. We start with x0. Let me check with x0. X0 here, assume that x0 is coming from the data distribution. It means that you trigger each of these algorithms using one data sample from your training data, okay? So x0 is coming from p data, as I write at the end of this line. Then you will start the iteration. You will have iteration number 1. So you reach a point which we call it x1. Okay, this is the output after one iteration. We know that. Assume that I have a bunch of samples of CIFAR 10 dataset here. This is our training samples of CIFAR 10. Okay. Assume that I use MALA or MH, and I apply one iteration with using a model which is not trained yet. Okay, so I have different samples here. Each of them has a corresponding sample here. The cloud of points here has a new distribution. Okay, we call that new distribution p theta of 1. So x1 is coming from p theta of 1 of x. Why we use theta here? Why is p theta 1? The first one is a fixed distribution because it is coming from the data distribution. The second one is a function of your model. Why? Because you apply one iteration. When applying one iteration, it means that you use the gradient of the energy. So it is a function of the parameter. It means that how this point is changed in the new in the new space is a dependent of the theta parameter. Does it make sense? So any of these, so we can continue this procedure. In the general case, in the TIF iteration, your data are coming from this distribution. And we know that if we continue this procedure at the end, what is the end? What is this distribution after, for example, a large enough number of iterations? What? This is the true model distribution, because you run Markov chain Monte Carlo methods for large enough iterations. Okay, so at the end you have the true model distribution. It is p theta of x. We want to sample from this one in the previous session, if you remember. Okay. Does it make sense? Everything? You start with the true data distribution, as I write it here. Then trigger a Monte Carlo Markov chain Monte Carlo method or algorithm. Each of the steps has its own distribution. We call it pt theta of x for the TIF iteration. But if this t value approaches infinity, it means that you have give enough iterations to your algorithms, and it is convergent now. It is converged to the true model distribution now. Does it make sense? These algorithms, MALA or MH, are guaranteed to converge to the model distribution. They are guaranteed, but you do not know what is the specific t that you can confidently claim that the resulting distribution is the model distribution. But if you give it enough time, or in an assumption, give it infinite number of iterations, it means that it is confidently converged to the model distribution. So at the end, p theta of infinity is equal p theta of x. Yes.
So what I don't understand is, iteratively, is it that you keep sampling from P of data and then take gradient and then optimize PT of theta, or what exactly is happening?
Yeah. Assume that I just want to talk about one sample, okay? I start one sample of, for example, MNIST. Okay? I have a randomly initialized model. The theta is randomly initialized, okay? If I apply, for example, MALA is the second one that we talk about. It uses the gradient information. What do you think we have in the second image?
It will still be that, but
slightly changed and some noise added, because you take the gradient of something which is initialized randomly and then use it to update your model. So you have something maybe noisier than this version. For example, these are the stand for nodes, okay? If I continue this procedure for infinite number of iterations, what do you think about the last image?
the same as the first one.
The model is not trained. The model is a garbage model. Now,
Noise.
yeah, it's random noise. You are taking the gradient with the direction of a model which is not trained yet. It is randomly. This is not your training. This is just sampling. This is not training. We want to train the model. This is the procedure how we train the model. This is just the procedure how you can sample. You can start from a random data and using MALA or Metropolis testing to sample, or you can start from data distribution. Each of them, if you give your algorithm enough steps, it will converge to the p theta of x. Here, because the model is randomly initialized, the last one is random noise. Random noise or something which is not understandable. Does it make sense? Yes.
So the difference between this method, the CD and like NH, the Hamiltonian, is that in MH we started with like a normal distribution, and here we just start with data distribution.
Don't make them confused. CD is a method for training energy-based model. MH and MALA are algorithms to sample from a trained model or any model, any energy-based model. So they're completely different, okay? Here I use I want to use an energy-based model using CD, okay? I said that if I sample the first sample from the data, I pick a data sample, then after T iteration, I can claim that I have a new distribution, P theta T of X, and this new distribution is a function of your energy model now because you take some steps using its gradient. For example, in MALA. Assume that you use MALA. Forget about the MH, because in MALA, it is definite that you are using the gradient of energy. Okay? So, if the model is a garbage model, during this procedure, I add something which is not going to the direction of increasing the probability. Because the model is garbage. It may have something irrelevant, okay? So after enough iterations, you have something like noise here. Because the model is still random. During this procedure, we train the model, and you will see how it will change. But here, what was the problem that I forget this approach? What was the problem that I forget this approach? Because if I can calculate the gradient of log of the normalizing, the partition function, then everything is solved, because I can easily update the model using this gradient. Why I forget about this model? Why I forget about this approach?
Is it time consuming?
What?
Time consuming.
Yeah, because if I need to calculate this gradient, I need to sample from the true model. True model. Pay attention to the keyword. True model, not data. True model. If you want to sample from the data, it is easy. You sample from training data. If you want to sample from a model, it is based on the model. If the model is, for example, BAE, it is easy. If it is GAN, it is easy. If it is, for example, autoregressive, it may be sequential, but it is easy. But if it is something like energy-based model, it is very hard. Because you need to run a Markov chain Monte Carlo algorithms for enough number of iterations, and then you are confident that the resulting sample is coming from the model distribution. So we forget about this method because this sampling is time-consuming. Okay? So put MALA or MH in one side and CD in another side, okay? Now we want to talk about how CD solved the problem, okay? Just this definition, these are very important definitions. The first one is that you start from a sample coming from the true data distribution. It means sampling from the data set. Assume that the model is not trained, you take one MALA iteration. You have something which is worse than this data. Why? Because this data is a true data. So it's in the point that must have high probability. But because your model is not trained yet, you see something like this, a noisier version. Because your model is not trained, it moves you toward a direction that do not increase the likelihood of a true data. So it decreases to some extent like this. But I want to name it, to put a name for this new data. I assume that the new data distribution is P theta of X. Just pay attention to the definition of this distribution. What this distribution said, assume that you have a model, energy-based model. After one iteration, you have a new distribution. That distribution is P1 of theta of X. And in general, at the iteration T, you have p theta t of x. Okay?
My question is, what's the point on like the latter one that you were explaining to like ignore? I was using the Mala or MH iteratively. Here we are also doing that one.
Yeah.
And you know what's the pros and cons of doing that one?
Yeah, we will show that you can use data coming from p theta 1 in CD. It means that you just need to take one iteration using Mala, and then everything works. This is the point. You do not need to stay until this point. Okay? We will see how, but just pay attention to the definition. At the t iteration, the distribution is this one. And if you wait until the infinite number of iterations, these two, the first one, the 0 is p data, and it is not a function of theta because you do not have any iteration yet. So it is the data samples. If you wait until enough iterations, or in an ideal case, if you wait for infinite number of iterations, then you are truly at the model distribution. So p theta of infinity equals p theta. Then CD is defined as this definition. This is the point. CD is this loss. Excuse me. This is CD because we generally maximize. Okay. What does it make? Does it make sense for you? It said that the CD with index t is the KL distance between the data and model. What is this? This is equivalent to maximum likelihood because we previously used this function as our distance metric. Yes? So, this is our previous distance metric. We have previously shown in the first presentation. We have previously shown that the KL between the data and theta, what is it? Equals to what expectation? Expectation of something with respect to something. What is here? Yeah, x coming from p data of log of p theta of this x. We know that they are equivalent. They are exactly the same. So in CD, the first one is exactly the previous one minus another KL divergence. The KL divergence between the tth iteration and the last iteration, because we know that p theta is equal to p theta infinity. So I can rewrite the above as this definition, and all of them it can be interpreted in terms of the algorithm you are using to sample, for example, Mala, okay? KL of P0, we know that P0 is P data, because you start with sampling from the data set sample. P theta is P infinity theta. Why? Because if you stay enough, you are at your model distribution. P theta t is still itself, but P theta is still P theta of infinity because, again, you know that if you stay for a large number of iterations, then you are at the model distribution. Everything is clear between the equality of these two losses. Clear? Yes.
But we don't know the P infinity.
Yes. We do not want to calculate samples from P infinity. This is the trick that CD wants to apply. Yes.
At the final stage, the P theta that we want is the normalized version.
We do not find the P theta. We just find samples.
Samples.
Yeah. That samples from the
So you don't care if it's normalized or unnormalized because you just want the samples.
Yeah, and those samples are coming from
the truth.
Yeah, true model distributions, which is normalized version. Yeah. Everything is clear with this equality? Yes.
So the second equation on the right-hand side, that KLBT of theta, is that just going to collapse to at 0?
No. You will see that when the model converts, there is something about that KN. Yeah. Okay, now think about this contrast, this visualization of CD. It may help you to understand what is happening, okay? We are at the point P0, which is equal to P data, okay? P theta is something here, just visually. So it is different from the model, from the data distribution, and this is something here. P infinity is there. The distances are meaningful. It means that P infinity and P data and P theta, P data, P theta T and P infinity are conceptually are in these distances. It means that P theta T is near to the P data, while this one is far. Okay, does it make sense? Because you start to changes P data through your iterations to transfer from the data distribution to model distribution. This is what Mala do for you. So in the second one, you are in the T iteration, you are near to data. Maybe the T iteration is here, but the most important point is that P theta T is something between these two. Does it make sense? Clear? Okay. And based on these positions, what is CD? The KL between P0 and P theta T, sorry. The notation is not correct here. This is P0 and P theta infinity, not T. They are, yeah. These two should be changed. This is here, this is there. Sorry, let me check. PT, no, the above is correct, just this one is not correct. This is P0 and P theta. This T is extra there, okay? So these are two terms that constitute the CD, and very steady.
The difference?
Yeah, exactly. CD is here. This is CD. CD monitors how you escape from the first distribution, from the data distributions, when you have T iterations of Mala or any MCMC method. Assume that in some case your model distribution is exactly your data distribution. What do you think of iterations? You are at some place that your model is exactly data. You start from data, and if you iterate through the Mala algorithms, then you reach the model distributions. When they are at the same point, what happens if you take one iteration? No, I just want to know whether the image, assume that you have an image, and the model and the data are exactly the same. Does this image change?
No.
No. Why? Because this point is high probability in both data and model, because they are exactly the same. And if you have one iteration using Mala, then nothing will change, because it is primarily a high probability point. Does it make sense? This is exactly the intuition behind the CD, and we will see now how it works. Okay, the first property of CD is that CD is non-negative. Why? Because, any question? Because the distance between data and theta and P theta T of P theta, let me check then. Yeah, it's okay. The distance between data and theta is larger than P theta T and P theta. It is exactly what you see here. This distance is always smaller than this distance. So CD is always positive. Okay? It is a good loss metric because it is always positive. If the zero, when CD is zero, when they collapse, they are exactly the same, the distributions, then it's a great distance. Yes?
Point that you mentioned that when P data and P theta are the same, the CD zero happens when We calculate KL exactly, not its estimation.
Yes, yes. We have the problem of estimation, yeah.
But then how we can calculate KL without knowing?
Oh yeah, we will see. We will see how you can calculate KL without having the end distribution. But you have the data distribution and you have the p theta t. Because p theta t is easy. You take just t iterations. You are confident that t iteration is enough. And t can be selected just one. It means that you just apply one iteration to your data and then you have the new sample to calculate your expectation. Do you have a question?
So the KL of like p theta t comes out like 1. It should be larger than the times out t plus 1, right?
Yeah.
The KL is true.
The KL between p theta t and p theta or p data?
So I'm talking about like 2 times that 1 is let's say t equal to 1, right? And then another times that's t equal to 2. And then the distance is larger, the KL is larger when it's t equal to 1.
The KL
is like that, keep decreasing like the KLs.
Yeah, the KL between the new point you get and the point you start, which is the data distribution, is increasing because you are because the Mala algorithms transfer you from the starting distributions to the end distribution. The starting distribution is data, the end distribution is theta. When you iterate through Mala, you are escaping from the data distribution and you are approaching the model distribution. Does it make sense?
Yes. And yeah.
Let me write something.
Where every single step will always be.
No, that's not a very precise.
But you will always decrease, right? For every iterations.
Decrease what?
Like the KL will decrease every iterations. So and then in infinity it converges to
the model distribution. Yeah. You know, it's something like this. You are starting from the data. This is just a simplification of what happened in practice. As you say, it is not monotonically, and you cannot claim on that, okay? But we know that the gradient, because you know that the Mala have some randomness and something like that. But in terms of distributions, everything works. In terms of distributions, not a data point. You should think of distributions. It means that the average over lots of samples, okay? Not in terms of one data point. Do not measure it in that case, okay? You start with p data. Assume that I start with 1 million samples of p data, okay? I transfer all of these 1 million into another cloud of points. Again, I have 1 million data, and those data are coming from a new distribution that I denoted by p theta of x. The P1. The distance between P1 and P data, and then I take another iteration. The 1 million data transferred to the P, consider a new distribution P theta 2 of x. The distribution here, but the KL between these two distributions is higher than these two distributions. Because Mala is doing the same. Mala is transferring you from the data distributions to another distribution, p theta. By how? By using the information of the gradient of this e theta of x. This e theta of x is corresponding to this p theta. This is if you calculate the gradient of the we have calculated previously. If you calculate the gradient of the log of this p theta of x, you will see that you have the minus gradient of e theta of x. We have it in the previous slides, okay? Why you transfer from this data to this data? Because you are using the information corresponding to the target distribution. Any question? Okay. If p data and p theta are equal, then MCMC algorithms, which is not the topic of this course, guarantees that p theta t equals p data equals p theta, and thus CD equals to 0. This is the most important point. If we have conceptually talked about this property. If let me talk it up again. I start with something which is coming from the data. And I am confident that after infinity iterations, I am at the point that the data are coming from p theta. This direction is the direction that increase the probability of samples here, because these samples here are high probability samples in data distributions. Here you will get samples high probability in theta distribution. Okay? This path, what happened to this path if they are equal? It means that something which is here is high probability here. So you do not need to do anything in between. And everything you do in between do not change the distributions because you are already at your target distributions. In other words, what happened to this e theta of x? Not precisely, but in the expectation mean, it is equal to 0, because you are at the peak of the distribution, and at the peak the gradient is 0. So it do not change you anywhere. Just the randomness is applied. The randomness using V, if you remember Mala, okay? And that randomness is just playing around the peak, not changing you from the peak, because the peak is the peak for both the data and the theta. Does it make sense? Okay. Another property of CD is that if you take the limit of CD for t approaching infinity, you have your original distance metric. It means the KL. We know that if you stay for enough number of iterations, then you have something coming from the model, the model distribution, and then you are calculating KL. Why? Because if you stay for enough iterations, this point coincides with this point, and the above term is 0, the below is exactly the KL divergence between the data distribution and model distribution. So CD has some interesting property. First, positivity. Second, it is 0 when they are equal. Third, if you increase t, you are at your previous distance. It means that the KL distance, or equivalently the maximum likelihood regime. Okay? Everything is clear? Yes.
Can we have a formal proof for the non-negativity property? Because
yes, that
KL is not a distance metric, and you're just explaining it intuitively, so it makes sense, but then KL is not a distance metric.
That's a divergence metric to some extent between distributions. You know, if you consider that cloud of points, that cloud is here at the data distribution, then you take one iteration, it's here in a new point. Think of not one sample, think of the distribution, okay? Using the MCMC properties, you can show that. You can show that if you take one iteration through the direction that the algorithms gives you, you are definitely approaching the target distribution in the sense of KL. Does it make sense? But the proof is not the topic of our course. Yeah, it is very complicated. pay attention to the fact that you are using the gradient of the energy of the target distribution. So you are changing the data so that they place in the peak position of the your target distribution, which is p theta. This is important. You change the samples so that the probability in the p theta distribution is increasing. So you are approaching. Okay? Everything is clear? Now we have another problem. How we can calculate this gradient? Because to update your model parameters, you need to, for example, minimize CDT. So you need the gradient. And the gradient is still the gradient of the scale of p theta and p data. P data and p theta, which is interactive, we know. And it is hard to calculate. The second one we will talk about. We will see that in calculating this gradient, the terms corresponding to the partition function will cancel each other, and then you get rid of the partition function. That the problem with this gradient, the first part, is the partition function. When you have two of them, the partition function will appear here, and they cancel each other. And you will see a very, very intuitive loss function. This is just math, and I know that it may not be interesting for you, but we should reach a point that to see how the partition function cancels each other. So let's start. It was better to be sequential, but assume just the first line, okay? Assume just the first line. I want to calculate each of these two gradients separately. Now I'm focused on the first one. We have previously just a recap of what we have previously, okay? The gradient of the KL between p data and p theta, we know that the definition of the KL is this one, and I denote it by A of p data and p theta. I want to calculate the gradient with respect to the model parameters, okay? So what happened? First, using the chain rule, I take the gradient, I differentiate A with respect to p data, and then take the gradient of p data with respect to the model parameters. Second, I take this differentiation or this gradient A with respect to p theta, and then take the gradient of p theta of x. This is just math, nothing more, okay? But we have a point. What is the gradient of p data with respect to theta? It is 0, because it's the data distribution. So I just have the first one. Now I calculate this term, the differential of A with respect to p data here, just taking the gradient of this term with respect to p data. We can calculate it as this one. What happened next? I preserve it here, but put this p theta of x behind this term and the minus 1. I have this one. Do not pay attention to the upper statement. This ratio is the minus the gradient with respect to theta of the log. So this is just a chain rule that we have previously seen in this course. And now, what do we have? We have the minus the gradient of the log. We have previously seen that the minus the gradient of the log. We have proved this part. This is coming from the definition of the energy-based model. It is very simple. P theta of x equals minus the gradient of energy minus the gradient of the log of partition function. Just use this equality here. The minus term makes both terms positive, the minus here, okay? So what do we have? We have, as we expect, because we calculated this part before, we have the expectation with the samples coming from the data distribution of this term, which is very easy to calculate. because expectation is with respect to the data, but we have this challenging term. So the first gradient equals the expectation with respect to the data coming from the true data distribution of this this gradient plus this the gradient of the log of the normalizing function, the partition function. Sorry. This is the first term. The first term is easy, but the second term is a bit challenging. All of them are not important for us, but pay attention to the approach that we reach the end point. Okay. Just I give you a higher intuition how we can calculate this gradient. I have the gradient, the gradient vector with respect to the model parameters of this integral. This integral is the KL between these two distributions. So it is the average or the expectation over the first one of the log ratio. The expectation, this is the expectation of the log ratio. Okay, if we denote it by P of P theta T and P theta, the problem here is that both of them are function of your parameters, okay? Again, if I use the pure math, I have the differential of B with respect to the P theta T times the gradient of P theta T of X plus the differential of B with respect to the P theta of the gradient of P theta T, P theta X. This is the last one, P theta infinity it is. Then we can do this integral is a linear operator. We can separate these two terms, the first term, the second term. We do not have anything in the first term. The first term will appear at the end, but the second term can be simplified exactly as before. Exactly as before. The differential of B with respect to P theta is this ratio. I put the minus and the denominator in the second part. This gradient, this ratio is the minus the gradient of the log of the P theta, okay? And this is equivalent to something like a grade, like an expectation. And we know that the P theta of X, then minus the gradient of the log of the P theta is equal, using this equality, is equal to this, the summation of these two terms. And finally, I have the first integral. The second one is the expectation with respect to the data coming from the model distribution at iteration T and this partition function. Okay. Yes.
Can you go back to one more slide?
Yes.
Shouldn't the last term be expected value of X?
This?
Yeah.
No. You know what? Pay attention to the variable of integral, okay? You have the integral of x p data of x of, sorry, yeah, I can write it. The gradient with respect to theta of e theta of x plus gradient with respect to theta of log of z theta dx. This is important. The first part constitute to the expectation x coming from p data of this term. But the second one, because this term is not a function of x, it can go outside and you have the integral of p data of x with dx. So it's equal to 1 and you have just the, yeah, you do not have the expectation. Yes?
When we update the theta, do we have to run the MCMC again?
Yes.
To calculate P?
Yes, yes. Everything should be run, yeah. That's the problem, because if you want to use the first approach, every time, every update, you should go to the infinity iterations and then find the true model distribution. Okay, pay attention. These two terms, these three terms, if I put them together here, the gradient of CD with respect to the model parameters is the, this is just the rewritten both of the things that we had before. The first row is the first term, the second row is the second term, and you can see that we get rid of z theta. Do you see? The log of z theta. plus minus, they can cancel. But we have another problem. But can you mention that problem? What is the new problem? Yeah, the integral is the problem. Why? Because you will see that you will have the p theta infinity here. Why? Because b is a function of p theta. B is a function of p theta. It means that is a function of the final distribution, which we will always escaping from, because we do not want to run MCMC for infinity iterations. And it appears here. So you have the problem. But if you see, there is a nice paper by Jeffrey Hinton that he showed that in practice you can ignore this term. You can find they evaluate this term in an application and show that how you can escape this term. You can find some information at that reference. Okay, what happened? You ignore this integral. The gradient of the log of the partition function cancel each other. You have just two expectations. What is new? We still need to use data from MCMC. What changes? What is changed? Yeah, you just need to select a T and sample and iterate using MCMC until that iteration. It is not needed to wait until the MCMC converge. Just, for example, select T equal to 1. Just have one iteration of MCMC, you have your samples to calculate the expectation. Does it make sense? It is much more easier than calculating the true model distribution, samples coming from the true model distribution. We tolerate these to ignore this integral and those to change this expectation from x coming from p theta of x into x coming from p theta t of x. Yes?
Can we ignore the integral because it just gets really small?
Yeah, that's just the problem. Yeah, you have find some justification in that reference, but the main justification is that it's small. Yeah. But you will see that how this new this new form will preserve the volume of the distribution. Because we know that the partition function is responsible to preserve your volume, not to go, for example, more than the unit volume. We will see that how it preserves the volume. Does it make sense how CD can relax the problem? Okay. So let's think of CD in the new form. Okay. Assume that I replace these two expectations with just one sample. Then I have something like this. The gradient of the CD with respect to the model parameters is the gradient of energy with respect to the model for data coming from the data. Why? Because this expectation is with respect to the data, the first one. Okay. The second one is the gradient of energy with respect to another point. That point is coming from the p theta t of x, and we know that it is simple. You just run MCMC for one iteration, and then you can use that here. Okay. If I update the model parameters such that it decreases this loss CDT, what happened? We know that we are going to the direction of energy. We are going to the direction that increase energy. Decrease energy at xd. Why? Because you are taking the gradient in the negative of this direction. So you are increasing the energy at this point and decreasing energy at this point. Let me rewrite it here. The gradient of CDT equals E theta in XD. XD means X data minus E theta of X theta. X theta means data coming from the model distribution. Okay. So what are you doing? You take the gradient into the direction of negative of this value. So you are decreasing this one. You are decreasing the energy at XD, and you are increasing energy at X theta. Does it make sense? And do you agree? Because of the gradient, you take the negative of this gradient. It means that with respect to this part, you are because this is the gradient of energy. You are decreasing the energy because you are going toward the negative of the direction of the gradient at this point. It means that at this point you want to decrease the energy. At this point you want to increase the energy. Okay? So in terms of energy, you are doing these two operations. But what happened in terms of log likelihood? Decreasing energy means increasing likelihood. Increasing energy means the vice versa, decreasing the likelihood. What happened? CD tries to decrease the energy in a point coming from the true data distribution and increasing for data coming from the model distribution. Pay attention to this image. The blue one is the model. The red one are the samples. Okay? Let's think of this gradient. What happened in terms of the log likelihood? Okay? In terms of the log likelihood. What happened to this region if I apply CD? Because when I sample from the model distributions, X theta, one possible X theta is here. Do you agree? Why? Because the model is high here, okay? What happened to this X theta, to the likelihood of X theta when I update based on CD? What do you think of this curve in this point? It decreases. Exactly. Why? Because this gradient said that it should increase the energy or decrease the likelihood. And the blue curve is likelihood or something like that because it is the p theta, not the log of p theta. Okay? So what happened? It decreased. XD is something like this because you sample from the model distribution, and these are the model samples, the training samples, okay? What happened? The blue curve here, it increased. Why? Because CD said that you should increase E theta of XD. Increasing E theta means that decreasing E theta means that increasing the likelihood. So something like this will happen. You decrease at the point, the blue curve is decrease at this point, and it is increase at this point, and you have something like that curve there. Here, it was a giant peak, but it is not giant anymore. Here, it was almost zero, but it is give probability using CD. So what happened? How CD is preserving the volume?
It's using the number amount of the density in the points that
the model is giving high probability. Yeah.
And can we say that for
any point other than XD, after the update, the density is decreasing?
It depends. For example, how many samples you are using to take the gradient, to take the expectation. Here I just use one samples from each of them. Yeah. So instead of just focusing on your true data samples and increasing the likelihood there, you at the same time increase the likelihood there, but decrease the likelihood at the other points that the model is previously giving high probability. It means that there is some budget here, you transfer it to here. You do not just increase your budget here and do not affect this point. Not only you decrease here, not only you increase here, you decrease here to have some balanced, for example, balance, or to have something unitary. This is the intuition behind CD. And I hope you get it all. Any question?
Does it change by the same amount, or can you do something?
No, that's not guaranteed. You know, at the end of the day, you do not come with the distribution which is normalized, but you come with a more meaningful method to update your model. Yeah, you cannot guarantee that the model is normalized, because you can see that we do not do anything with the normalization and the partition function. Partition function was cancelled using the CD. Yeah.
So in this method, we just generate like p theta 1, and then update the gradient like for a couple of times, and then we have a model that gives high probability to points where the actual data distribution is also giving high probability.
Yeah.
And
But pay attention that these are just visualization. We know that. For example, using Monte Carlo methods, you cannot go exactly to the high probability point of your data. But this is just a justification how it works. It is not exactly what happened in practice here.
yeah. So in the bracket, no bracket, yes, the first row, yeah. So here the expectation was on p data. Okay, so it's the
P data? Yes, so I have XD.
yeah. But why we put the XD in p theta?
P theta? You know, E theta is corresponding to your model distribution. It's the energy corresponding to your model distribution. We do not access to P theta, but we can infer that if the energy, yeah, we do not access here. We cannot evaluate this. This is not normal. We just have energy. Any question? Okay. And this is just a visualization of, and this is very interesting example. We trained, I think it's exactly from the same, let me check it. Oh no, I think it was from the Jeffrey paper, but it's from this source. Maybe it's their next publication, which is a more complete version. We can find the source. What happened here? I start. I have the energy function for an MNIST. I assume an energy function for MNIST, and then I start training that energy function using CD. Using CD, it means that I sample from the true data distribution, T iterations of the MALA, then taking the gradient, and exactly the same procedure that we talked about. At the end of the day, you have a new model. You have a model. That model gives you the direction that if you follow, you will be increased in terms of the likelihood of the data, the model. But then, because the model is trained, so you can easily find you can easily sample from that model. And what are these samples? Assume that we have a trained model. Now we know how you can have a trained model using CD, for example. Okay? We have a trained model. Then I can start from a random point and take the iterations using MALA, and then at the end of the day, you have a sample from the model distribution. And because the model is trained, the samples are similar to the true data distributions the model is trained on. This is just one sampling, one MCMC algorithm. Starting from random noise, because you are using the energy function and information there, you are updating so that you will reach some meaningful point. And this is just sampling, not training, okay? This index is the iteration. And you can see that using reasonable number of iterations, you will have acceptable samples. Yes.
So in this EBM training, what can we like intuitively say in what iteration did the training happen?
This is not training.
No, I know. Like since it took, for example, 256 iteration to generate like a well-shaped number, can we say that the training has also been used for?
You know, because the X0 during the training you sample from the training data, but here you sample from the random data. The random noise. No. You start with random noise. This is different. In the training, you know, why do we use the data distribution in the training? Let me check. That's an important point, you know. Here, in the training, X0 is coming from the data distribution. It makes the learning severe for the model. Why? Because you tell the model that in a point, assume that the next one x1. We know that x1 and x0 are not very different in terms of their visual concept, because you take just one sample, okay? But the model, the energy-based model, during the training must decrease the probability here and increase it here during the training. It's a challenging task. Why? Because they are almost similar. You just take one sample. Assume that I use t equal to 1 in the training. It means that I use CD1. Your model should discriminate, should increase the probability here and should decrease the probability here and increase it here. It is a hard task. Why? Because they are almost similar. You want to, but here it is completely different. You start with random noise. If you start with random noise there, you will have some problems in training. In the training, you start from the data samples, which is the high probability samples in the true data distribution.
So my question was like, usually how many iterations do you use to train the model?
Oh, but for training,
Yeah.
I think even the t equals to 1 works in practice. Yeah. Any question? Okay.
So these are the images that xt changes over different iterations, not the process of x for the trained model. So you have two different iterations. One, we have found the optimal theta, and to find a p of the theta of t. So we just start from x0 until we find xt. So these numbers are not x0 to xt. These are the xt over different iterations, right?
Yes, and also the starting point is changed now. During the training, you start from x0 coming from the data again, okay? But here you start from Gaussian noise. This is during the sampling, as here. This is during the training. Does it make sense? Because if you start from this point, you are at a low probability point of the both data distribution in the training, I'd say, and the model. But this works better for the training, okay? But during the sampling, all the methods that we will talk about from now on, for example, energy-based model, diffusion model, start from the random noise. They start from random noise, and because they have the energy function, they can change their x input x so that the energy is minimized, or equivalently the likelihood is maximized through one of the MCMC methods. Yeah. Okay, I think we can now start the next part. Today we have the office hour, exactly just after this class, and also we have another office hour tomorrow, I think 3 to 4, but check the canvas for the time. Both of them are the room 20507. Any question? Okay, thank you very much.